Draw a graph that models the connecting relationships in the floor plan below. So here we have a floor plan for a house. The vertices represent the rooms. So this is a room, this is a room, this is a room. And the edges represent doorways. So there's a doorway, 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 connecting the rooms. Vertex D is the outdoors. So this just represents all the outside. D does. D is anywhere outside. Okay, so that's what they're saying. So let's do this. We want to figure out, well, let me get down to the question. I better get to that. Is it possible to find a circuit through the house that uses each doorway once? If so, enter the sequence of rooms, vertices, visited. For example, A, B, C, D, A. If it is not possible, enter D and E does not exist. So what are they saying? Is it possible to find a circuit through the house that uses each doorway once? In other words, is there a way to go through the house going through each doorway once? Like, for example, I could start out here, go through this door, this door, this door, come around, this door, and I'm back outside. So yes, there it is right there. Do you see that? That's a circuit that went through each doorway only once. I didn't have to go twice through any door. And it made a circuit, it made a circle. Now, this one's somewhat of an easy example. They can get harder and more tricky. So let me give you all the mathematical stuff behind this circuit that we can see is our answer. How do we, if they're harder, how are we going to be able to tell? Make each of these a point. So A is a point, D is a point, B is a point, C is a point. So each of the rooms and the outdoors, D, remember D represents all outdoors. That D is everywhere outdoors. It's not different to be over here outdoors than up here outdoors, or over here or down there. Those are all one place. D. You can put D over here, down here, up there. D is all the outdoors, is what they're saying. So it's just one place, all outdoors. And then there's three other rooms, A, B, and C. So altogether we have 4 locations. Outdoors, D, and then A, B, C for the 3 indoor rooms. And now let's connect those dots by their doorways. So A, notice, connects through this door out to D. A connects through this door to C. C connects through this door to D. B connects through this door to D, because that goes outdoors, and B connects through this door to D. Okay, so that's really our graph. Let me redraw it a little, maybe a little nicer. So here's D. Here's A. B and C. So looks like A has one line up to D. That's this line right here. And then one line down to C, that's that line right there. And then C goes up to D. C goes up to D. And then B has 2 lines going to D. And nothing else. So over here now is a simpler version of our household. Our house and the paths between rooms and outdoors. So now that's a graph. So now looking at that graph, let's determine this graph right here is an Euler circuit possible. How do you know if an Euler circuit is possible when you're looking at a graph? Only, let's just say all vertices, oops, spelling that wrong, even degree. Let's see it. This is a 2, right? There's 2 lines hitting at that point, 2 lines hitting at that point. What do we got? 4 lines hitting at this point, 2 at that one. Look at that. All of the degrees, every vertex has an even degree. So yes, it's possible. Now, other examples you might get in the homework is an Euler path. When is an Euler path possible? Let's make sure you know that. That's not this question, but there's other versions of it. It's when you have only 2 odd vertices and all others are even degree. These are degrees. So when you have only 2 odd degree vertices, so for example, if you had 1, 2, 3, that would be a very simple one because this is 3, this is 3, this is 2. In fact, you could even put one here that's 2 and one here that's 2. So you have exactly 2 vertices with odd degree. There's going to be an Euler path possible, and you must start and end at odd degree vertices. So to make an Euler path, when you've got 2 odd degree vertices, which is what you have an Euler path, you've got to start and end at those odd degree vertices. But anyway, that's not our particular problem. So what if you have more than 2? So we said if they're all even, then an Euler circuit is possible. If only 2 are odd, then you can have an Euler path. But if there's 1 or 3 or more odd degree vertices, then there's neither an Euler path nor circuit that are possible. Can't be done. So you have to have all even for an Euler circuit or just 2 odd for an Euler path. Okay, so in our case we have all even, don't we? Even degree. All the vertices are even degree. So therefore, yes, our answer is yes, we're going to have an Euler circuit here. We don't need to say D and E. We're going to have an Euler circuit. Now, how do you find the Euler circuit? Well, basically, start anywhere you want. Let me just start right here at C, for example. And I'll go up here to D, so C to D. And then from D, I'll go down to B. There's other ways you could do this. This is only one way. Back up to D. You got to just take every path. That's what an Euler path or circuit. You got to cover every road. Now down here to A. And then from A back to C. We made a circuit. We're back to where we started from. And we covered every connection. We went through every doorway is really what we just did. So this is one answer. There's many others. That's an Euler circuit, meaning it goes through every doorway. It takes every path. So in real life, you wouldn't care about moving through your house this way. But where this is very important and useful is all kinds of things in real life, like street cleaners, garbage men, post office, that have to cover every street. Right? Street cleaners got to clean every street. Postman's got to go every street and deliver the mail or pick up the mail, etc. Lots and lots of different times in real life we have to cover a route. We have to go on a route that covers every street. We can't miss any street. And we want to do that as efficiently as possible. We don't want to double up our streets unless we have to. So the question is there a way to go through every doorway, which is the same thing as going through every street. If this was a map of a bunch of houses or properties connected by various streets, it'd be the same exact issue. Is there a way to cover every street without repeating any streets? The answer is yes, and make a circuit. Yes, that's called an Euler circuit. It's possible if all the vertices are even degree. So here's one of the many possible Euler circuits.